How's everyone feeling? Mix of reactions. If things aren't great, I hope that improves. Let me know if you need anything, again, at absolutely any time. Does anyone have any questions or concerns right now? All right. Again, please interrupt me with anything you need at any time. Last week, we handed out that remote lab. On Friday, we began looking at Newton's third law. My plan for today is to finish that analysis, make sure Newton's third law makes sense, and then we will spend some time looking at what the rest of the week will be about. So today is finishing Newton's third law, beginning what the rest of the week will be about, which will be chapter 6 about collisions, basically, applying Newton's laws. And additionally, I just want to mention about the remote lab. All the work I've been seeing has been great. I've still been giving people feedback, and as long as you are showing me the lab and responding to feedback and then taking the time to implement said feedback, don't worry about any sort of a due date. I wanted to see everyone's work by around last Friday to make sure that we're working on it and give you your first batch of feedback. If it isn't handed in to me and perfect, that now that is totally fine, because I'm still giving people feedback, I'm still helping people out. So as long as you are still working on it, as long as I get it, I'd say ideally by the end of this week, but I don't know your schedule, I don't know when you have to work on it. As long as you are still implementing things and showing me your work as you go, everything's fine. We're doing it as intended. Speaking of lab, we're back to normal schedule. We have a normal lab this week, and it should be an interesting one because it does involve cannons. You'll be firing something across the room, what are my words, Brian? This is kind of the first big experiment where something's going to be moving and where there's any element of danger. I remind everyone to follow all lab safety rules this week, which include, but are not limited to, not shooting at other people. But labs will continue to be pretty interesting because we've got cannons this week and collisions next week. So stay tuned for that. Before we get started with lecture and notes and such, once again, how are you guys feeling, and does anyone need anything?
How are you feeling today?
Yes. My car issues from last week, I think, are still weighing on my brain, which is suboptimal. But I think I'm good. My brain started getting off on all the ways I could answer that question, but I think overall things are going very smoothly. Thank you for asking.
Yes, sir.
I don't think there's anything interesting to mention. I'm happy my 3D printer is working, because it was not working for a while and I got it fixed, and now I'm able to make some nice things for my wife and my friends. So that's a nice thing.
What's the last thing you printed?
I have been designing deck boxes for my wife. I have, and they're all different sizes. She has different ones for different reasons. Like one's for like journal prompts that you just draw something and then think about it. And I have to measure all of them because they're all different sizes, but they've been coming out pretty nice. And then I'm printing batarangs for my brother and a Jigglypuff for my friend because his wife hates when he plays Jigglypuff in Smash Bros.
My little brother just got a 3D printer. He's trying to figure out how to use it and everything.
It's fun, but at least mine had to be very specifically built, so it takes a lot of learning, at least in my experience. We actually have a bunch of them across the entire science department here. So if 3D printing interests you, talk to some of the physics majors and the physics club, basically. They've been teaching people how to use them. Actually, those two email addresses, the same people who do the tutoring, are also in the physics club. Anything else for right now? All right. Last last time we had begun looking at Newton's third law specifically. Last several chapters we've been looking at each of Newton's laws of motion one at a time. This is Newton's third laws, time to shine. To briefly look at the laws as a whole again, because you do have to know them by number. In order, they are 1, the law of inertia, 2, the law of acceleration, 3, the law of action and reaction. What this law tells us is that literally every single force ever will always have some reaction pair pointing in the opposite direction. That's true of every single force, because every force always has to be exerted by object A and acting on object B. You can't have a force that doesn't come from somewhere. Every force originates from something, and every force also has to act on something else. You cannot have a force with no source. You cannot have a force with no target. And by virtue of that fact, Newton's third law states that every target will then act back on the source of the original force. And it is always, if A on B, then B on A. Whatever A first does to object B, B will do the equal but opposite thing back to A in terms of force. And we call these pairs of forces action-reaction pairs, appropriately. And every force is a part of one of these. Every force has a pair. Because again, every force has to have an A acting on B structure. It comes from somewhere, it acts on something. So every force has one of these. Even if the reaction is weird, even if you don't notice the reaction, and actually those are the two main things. Even if you don't notice it, even if it's somehow weird to think that it exists, I promise it's there. And the main thing I'm going to do for this first half of lecture today is go over these scenarios to make sure that how the action-reaction pair works makes sense before we move on and apply it to other things. Namely, I gave you a few scenarios last time, and we looked at what exactly the pair was in each of these scenarios. You punch wood, wood punches you back, ball hits floor, floor hits ball. And the one we ended on, the weird one in my perspective, I've been trying to describe it as the weird one, I think. A rock falling towards the ground. Force of gravity is what's causing the rock to fall. And the third law pair to this one is what I find to be very interesting. That's going to kind of be the narrative through line as we explore how Newton's third law works and how its quirks interact. The main thing that I want to make sure you understand by the end of today is that normal force and gravity are not action-reaction pairs. So let's explore what that is. I have a list of 3 quirks related to Newton's third law that we're going to go through. The first quirk is a reminder that whatever object A does to B, B will exert the same force back on A, even if it doesn't seem like it does. Even if it doesn't seem like it does. It's the same force in both directions. The image I have on screen is of a vintage cannon being fired, and in this interaction, the cannon, via the explosion, exerts a certain amount of force forward on the cannonball, and according to Newton's third law, the cannonball must exert the same amount of force back on the cannon. Now, if you were to watch this happen, like say you were at some sort of historical event or watching a pirate movie, does it seem like the cannon receives the same amount of force as the cannonball? Now, why does it not seem that way?
Because the cannonball goes farther than the cannon.
Yeah, the cannonball goes flying by design. Frankly, that's kind of the point of a cannon. The whole point is to get this thing over there. And the cannon itself doesn't have quite the same reaction, right? Now, if you pay close attention to said pirate movies, you would probably notice the cannon does what we call recoil. It does get knocked slightly backwards, but not nearly as far backwards as the cannonball gets launched forwards, right? But it does get forced backwards slightly, and that is evidence of the reaction force. There is still a force acting from the cannonball back on the cannon. So let's say it's like a 2,000 Newton force pushing the cannonball forwards, and therefore there's a 2,000 Newton force on the poorly drawn cannon backwards. And I promise you that it is the same force in both directions. The different reaction is because these objects have very different masses. They're both probably made of something like cast iron. So if they're made of the same material, they'd have the same density, and the mass is therefore going to be up to their size. Cannonball is about this much cast iron. Cannon is like this much cast iron. It's a lot bigger. It's got a bigger mass. And the same force acting on different masses causes different accelerations. The same 2,000 Newton force acting on something with 1,000 times more mass creates 1,000 times smaller acceleration. So it's the same force acting on two very different masses to create two very different accelerations. To try to put some sample numbers in here, it'd be like 2,000 equals 2 times 1,000 versus 2,000 equals 2,000 times 1. See the difference? The different mass causes a different acceleration in the recipient, but it's still the same amount of force. Therefore, Newton's third law still works here. Similar scenarios would include, I'm about to throw this golf ball at the wall. So, slight noise ahead, just as a warning. 3, 2, 1. In the interaction of ball and wall, both will exert the same amount of force on each other. However, the golf ball accelerates a lot, and the wall accelerates nothing. The wall doesn't go anywhere, which is good, because if the wall went somewhere, the building would be in bad shape. The difference, again, is the mass of the two targets. This thing probably weighs like 10 grams. Whereas the building is several untold thousands of kilograms. So it does not accelerate noticeably from the same force, which again is good. If you have an accelerating building, you're in trouble. The entire purpose of buildings, and therefore architects, is net force equals 0. And if net force equals 0, net acceleration is 0. If any part of your building accelerates, your architect did a bad job. This is literally, I had to do classes about this. The entire point of an architect is to make sure all the math leads to this answer for every part of the building. They're designed such that acceleration equals 0. So again, very different mass, very different response to the same amount of force. The other example I listed here is if you hit a mosquito with your car, the 1 Newton force between the two is enough to obliterate the mosquito, and your car does nothing. So, makes sense? All right, so thing to note, the forces are always symmetrical, and they are always on opposite targets from one another. Quirk number 2 from Newton's third law that I'd like to make sure makes sense. By definition, normal force is a reaction force. Normal force, support force, something we've talked about before, by definition always happens as a byproduct of Newton's third law. Normal force happens because some surface got pressed into, therefore as a response the surface pushes back. We primarily looked at normal force up till now as just the force that keeps things from falling through the ground, the force that keeps you from crashing through your chair. In that case, similar to this boulder here. The boulder presses into the dirt. As a reaction to that, the dirt presses up on the boulder. And again, that supports the boulder, keeps it from burying itself and digging to the core. All normal forces work in this way. They are always a reaction to the surface being pressed into. But curiously, the surface doesn't really care if gravity is the reason why a surface is being pressed into. You see, bless you, bless you. In this scenario, the normal force is being caused by the dirt. The boulder is pushing into the dirt, so the dirt pushes back. Dirt is dumb, right? Dirt can't think for itself. The dirt doesn't know why something is pressing into the surface of the dirt. It just cares, I don't like that, I'm fighting you. It pushes back because you pushed into it. It doesn't care how or why that happened in the first place. This is similar, in my opinion, to a game that I assume other people would play at the supermarket. Those fruit hanging baskets that you put fruit in away, those still exist, right? At the grocery store. If you put, a kilogram of apples in there, it'll tell you the weight of a kilogram of apples. The way that works is the apples push into the scale, and as a response, the scale pushes back. And secretly, all a scale can ever tell you is the normal force it's exerting. Because again, scales, the dirt, they don't have brains. They can't think for themselves. They don't really know. They can't calculate, this is 3.2 kilograms. I'm going to multiply that by 10 and tell you the weight in newtons. No, they just know, I'm being pressed into this much. I will fight you on that, and I am designed to tell you the number that I'm pushing back with. All a scale tells you is the normal force it's exerting back on you, because that's all it can tell. It doesn't care how many things are pressing. It doesn't know how many things are pressing on it. It just knows 10 newtons of force down, I respond with 10 newtons up, and that's the number I read. Which is why, and again, this is the game that I and several people like me played as a kid, would grab the scale and just yank down on it, trying to max the number out, right? Sound familiar, please? I'm not the only one. Okay, so when you do that, you are putting more force into the scale, and it's going to exert more force back, so the number it reads increases. But again, that's not because of gravity, that's just because force on scale. The scale doesn't care if it's gravity or not, it just cares that something's acting on it, so it responds in kind. So normal force isn't specifically a reaction to gravity, it's just a reaction to something being pressed into, and therefore it pushes back. Similarly, if you lean on a wall, it pushing back is normal force, but it's not responding to gravity, it's just responding to me leaning into the wall. I'd say another example is if instead of a vegetable scale, you just have a bathroom scale that you are weighing yourself on. The scale doesn't really know how much you weigh, it just knows how much force is being pressed into it. And that's why, if you go on the scale with your shoes on, it reads about, the weight of your shoes bigger. You can't differentiate between you and your shoes. Furthermore, you can mess the number up by using the edge of the counter to either lift yourself up slightly, reducing the force going into the scale, therefore the number goes down, or by using the counter to press harder into the scale and the number goes up, even though you didn't gain 20 pounds in that moment. You're just pressing harder into the scale. Normal force only cares about how much force is being pushed into the surface. It doesn't care if gravity is the reason. It's just a response to a surface being acted on. Make sense? Furthermore, normal force is weird in that the surface can only respond to perpendicular forces. Do you remember when I said that normal force, when I use that term instead of support force, normal force uses the math definition of the word normal? What is the math, if you remember me saying that, what is the math definition of the word normal? That marker's dead. The math definition of normal is just perpendicular. They are total synonyms to a mathematician. Normal, perpendicular, orthogonal, they all mean right angle. Surfaces can only respond, they only create normal force perpendicularly out of themselves in a response to the forces acting perpendicularly into them. If you're on flat ground, you are pressing perpendicularly down into it, so it acts perpendicularly back up. If you lean on the wall, I push perpendicularly into the vertical surface, and it pushes perpendicularly back out. This causes a weird reaction on inclines. Because when you're on a slope, gravity still points down because Earth's core isn't anywhere different, just the surface you're standing on is different. So when you're on a slope like this, gravity is still pointing straight down, but it's no longer perpendicular to the surface. And the normal force, it only responds to the amount of force that is perpendicular to the surface, and that force is then still only perpendicular to the surface. This is proof that gravity and normal force aren't third law pairs, because they are neither equal nor opposite in this scenario. You see it? They aren't in the same direction anymore. And also, if we did the math for this, they wouldn't even be the same number anymore. They start forming like the sides of a right triangle. So this definition of normal force, my goal of bringing it up is to again point out normal force and gravity are not action-reaction pairs because they can be neither equal nor opposite. There are loads of scenarios where they aren't. The only time they are equal and opposite is if something is just sitting by itself on a flat surface. But if the surface tilts, they aren't opposite. If I add more force, they aren't equal anymore. Because the eraser's weight doesn't change, but the surface still has to push harder to overcome what I'm doing. So, gravity and normal force are not action-reaction pairs. And this interaction on the slope is actually the reason why things slide down ramps. Because if you add these two forces together, they don't add up to zero, they add up to this. And that's why you get pushed down a ramp. Make sense? Does that explain something? That's also why the greater the incline, the harder it is to, stick to it. So, trivia piece number 2. Normal force doesn't care what's pressing into something, it's just going to respond based on how much force it's being pressed into, because the surface doesn't know. Now, if normal force and gravity are not action-reaction pairs, what is the reaction pair to gravity? And the example we ended on Friday, Earth's, this is not to scale, by the way. This is not the meteor that killed the dinosaurs. This is just a stone and the Earth, so not to scale. The gravity of Earth on the rock is what causes this rock to fall. What is the reaction to this force, given the, if A, B, then BA structure? It's not normal force. Normal force is not the reaction to gravity. Gravity? Gravity is the reaction to gravity. If Earth's gravity is pulling on the rock, the reaction to that is the gravity of the rock pulling up on Earth. The reaction to gravity is more gravity. That's the third thing. Every object with mass exerts a gravitational field. That includes humans, by the way. So, you are in Earth's gravitational field. Earth's gravity affects you. Likewise, the Earth is in your gravitational field, and the Earth is subject to your gravity. And that is the reaction. If A on B, B on A, if Earth's gravity acts on my body, my gravity acts on the Earth's body. Earth pulls me towards Earth's core, I pull the Earth towards my core. Now, if that sounds weird, it's probably because you've never noticed it happen. So to kind of tie back into that first piece of trivia from earlier today, you don't notice this because the Earth is too big for our gravity to meaningfully interact with. Again, net force equals mass times acceleration. The mass of the Earth has, I forget how many zeros, at least 11. So, you know, if I weigh 1,000 newtons, the Earth's gravity is acting on me with 1,000 newtons of force. And that force on my mass causes an acceleration of 10 meters per second squared towards the ground. But that same 1,000 newtons acting on the Earth's mass would cause, you know, an acceleration of times 10 to the negative 11th. You're not going to notice it. I don't have enough gravity, enough mass to move the Earth around meaningfully, which is good. I don't want to knock the Earth out of its orbit. I live here. I kind of need it to be where it is. But this is why you only really notice the gravity of really big things. And that gravity mostly affects really small things. So the reaction to gravity is more gravity, and you only really notice it when a big thing is pulling on a small thing. However, again, you'll never notice your own gravity pulling on the Earth, but technically speaking, I could say Earth weighs 1,000 newtons on planet me, which is a statement. But there is one scenario where you can kind of notice this happening, and that's with the tides. You guys know how the tides work? Give me a very quick summary.
It's based off the moon, isn't it?
It is. The moon pulls on the Earth and causes the tides. So, still not to scale, by the way. The moon is way smaller and way further away. The Earth's gravity acts on the moon, pulling the moon towards us, and that's why the moon orbits us instead of flying away. Meanwhile, as a reaction, the moon's gravity acts on the Earth. So there is a force in both directions, but because the Earth is so big, the Earth itself doesn't accelerate because of this force. However, this force is strong enough to move the oceans, because the total mass of Earth's surface water is a lot smaller than the mass of the rock that we live on.
That's why we got waves.
Say again?
I said that's why we got waves.
That's one reason why we have waves, absolutely. So what happens is the moon is just constantly pulling most of Earth's water towards one side of the planet at any given time. And as the moon circles, this lump follows it. So if you're here, it's high tide, and if you're here, it's low tide.
Whatever happened if we lost the moon?
The oceans would stagnate, they would not be oxygenated, and everything living in them would die. And then we would die, because we get most of our oxygen from the ocean. Earth is literally like the perfect balancing point to support human life. If anything about this planet was slightly off, no. We need the moon, we need to be exactly as far from the sun as we are, we need exactly our strength of magnetic field, we need exactly the right combination of elements and things to be alive. It's kind of perfect here. I'm not sure how having multiple moons would mess it up, though. I guess 2 moons either side of each other would probably be fine. But right now the 1 is all we need. Yeah, without the moon, we'd be in trouble. Also, fringe benefit, the moon helps deflect meteors. Sometimes they crash into it instead of us. So another reason we want it. All right. All that to say, that's reason number 3. Gravity, normal force are not action reactions. The reaction to gravity is just more gravity. Make sense? Or feel all right at least? All right. So just to briefly summarize into one more quick example, here we have the same boulder picture I've been using for weeks. What forces are currently acting on this boulder? Very good. Normal force up and gravity down. These forces are not third law pairs for all of the reasons listed today, but I will draw them quickly once I find a marker. Thank goodness. I think I should throw away the dead ones, but someone stole my trash can. I don't have anywhere to put them. So these are the forces acting upon the boulder. So if I ask you what forces act on the rock, this is it, and you're done. Now separately, each of these 2 forces has their own reaction force. They aren't reactions to each other, they each have their own. So these are both acting on the boulder, which is further evidence that these 2 things aren't reactions to each other because they're both acting on the same item. And that means that it doesn't follow, if these were reactions, they wouldn't follow the ABBA structure. They have to act on 2 different things. So further proof, not pairs to each other. Instead, they each have their own pair. The pair to gravity is more gravity. If Earth's gravity on boulder then boulder's gravity on Earth. And separately, the reaction to this normal force, it would read as if the ground, my handwriting is awful today, I apologize, pushes up on the boulder, therefore, the boulder pushes down into the ground. So there's 2 forces on the boulder. Each of those 2 forces has their own pair. So we're describing 4 different forces here, but only 2 of them are acting upon the boulder. The other 2 are what the boulder does as a response. How's that feel? All right. So again, gravity, normal force are not action reaction pairs. Another neat takeaway is you have your own gravitational field, so you kind of have a superpower. You know, you give it long enough, you could cause something to drift into your hands. If there wasn't air resistance, if you had a year to wait. So, any questions about Newton's 3rd law for today? All right. Now, that is all of the laws covered, so we will now be spending the next couple of weeks applying them to various things before our first test. That is in a couple of weeks. I'll make sure to describe everything you need for it as it approaches, don't worry. But now I want us to look at the very least, set up what we're going to look at for the rest of the week, a specific application of these laws. So our next concept we will be studying, why is my account doing this? Is momentum, impulse, and collisions. The collisions part is going to be the application of the laws so far, because if things collide, they exert 3rd law forces on each other. So again, direct application. Any questions before we slightly switch gears into setting up chapter 6 for this week? All right. Now again, today we're really just setting up what the rest of the week is going to be about. And in order to do that, I want to make sure that you have the definition for momentum, since we're going to be saying it all week. Now, off the top of your head, what do you think momentum means?
Something constantly building up, or something that's like gaining a certain amount of like, I'm trying to use the word momentum.
It's okay, it's okay.
It's gaining something, or it's like ramping up.
Gaining something, ramping up. Yes, very good. Momentum is something that you do gain. The question, so that is absolutely true. And a rather frustrating thing about physics is there are some things that we can measure and describe that you can't see. Momentum is one of them. It's kind of like energy. You either have it, you do something with it, or you don't, and you don't. So it's kind of invisible, frustratingly. Now, so momentum is something that you can have. How do you hear the word momentum used when it comes up occasionally in American English? What contexts?
Like how much momentum, like if you're playing a sport, like your personal momentum of moving like forward with your body, or the momentum of like when I played softball, it's my momentum of like getting the base or hitting the ball, my personal force that I'm exerting.
Exactly. Very good. And I do find it kind of interesting that this physics concept is most often used in sports. But the way it's used in that context is pretty accurate. Momentum is something that you can have that contributes to your forward motion. So I often complain about how physics concepts get misused or redefined in English vernacular, but the way that momentum gets used is actually pretty accurate in my opinion. The definition of momentum that we're going to be using for this week is it's a vector measurement of something that you can have, which again is an apt description, like energy and momentum are just things you possess. It's a vector measurement of how difficult a moving object is to stop. The more momentum you have, the more difficult you are to stop, which is again why it gets brought up in sports. Because if you are an athlete charging forward, you are usually pretty hard to stop, and you usually don't want to be the thing that the athlete runs into. I've also heard it used kind of as a metaphor, like this team built up a lot of momentum this season, nothing can stand in their way. So even as a metaphor, it's still used pretty accurately in my opinion. Now, momentum is a vector that we can measure, and that means we can also calculate it. So it does have a new formula for us. Momentum equals mass times velocity. Now, an unfortunate trend in physics is that we ran out of letters for our algebra a long time ago. I understand and do appreciate the fact that there are 2 words that begin with M when I read this formula out loud. Momentum equals mass times velocity, and yet the only M present is just for mass, because, again, we ran out of letters. Uppercase M is used for mass in specific circumstances, so when we needed a letter for momentum, no version of M was available. And so instead, we stole a letter out of the Greek alphabet. The variable for momentum, this first one on this equation, is the Greek letter rho, which is not used in any Greek organizations on campus. So if you haven't heard it in a minute, it's spelled R-H-O if you're spelling the letter in English, rho. It is technically not a lowercase English p. No, English p is used for a different variable entirely, because of course it is. The differences are subtle, I admit. At least when I'm writing it out. P has this little stem on it. It kind of looks like letter D with this flat piece here that has a stem up and a long stem down. But rho is just a circle with a tail. It doesn't have the stem up here, and it's rounder most of the time, in my opinion. And they are further distinguished from uppercase P in that they are lowercase. Uppercase P is power. So we'll get to that next week. And I will always be very specific when I'm reading these out loud and try to make sure that they are kept straight. I'm personally never gonna say P equals MV because again, P is power. I'm gonna read out rho equals MV. Again, just to try to make sure that the variables are kept straight. I have had students express frustration with it being rho and not some form of M. And I do understand that complaint. If it helps, you are totally valid if you want to call it rho-mentum. I don't know, that helps some people. But our new formula for this is rho equals mass times velocity. So the two things that affect your momentum are mass and velocity. The bigger something is, the harder it is to stop. The faster something is moving, the harder it is to stop. So, to summarize the unit down here, momentum is the variable is lowercase rho. It is a vector, it does point in a direction. Namely, momentum has the same direction as the velocity. Since mass doesn't have a direction, the momentum just keeps the velocity's direction. So if you're moving north, your momentum wants you to keep moving north, for example. And momentum does not have its own dedicated unit, interestingly. Like we have grams for mass and newtons for force. The unit for momentum is just kilograms times meters per second. We never gave it its own. I assume the reason for that is, ironically, the European physicist that did the most work for momentum was also Newton. So we're kind of still on Newton's laws, actually. And we already put his name on the force unit. They could have called them Isaac's, because they had two names, but they opted not to for some reason. Now the unit's just kilograms meters per second, which at least thankfully is literally just the two units you multiply together when calculating it. So when in doubt, just follow the units in the formula. Speaking of that formula, since it is a new one, let's at least get a small amount of practice forward in your notes. I have currently on screen 4 different scenarios describing 4 different objects, or in one case organisms, with different masses and velocities. I'd like you guys to very quickly tell me which of these 4 scenarios has the most momentum in it. Got 1 vote for C. Anyone agree or disagree? A couple votes for B. That is the fastest one. Any other final answers? All right. Drum roll, please. It's C.
Told you.
I normally don't try to trick you, but I was a little tricky with units this time around. Again, the unit for momentum is kilogram meters per second, so you want to make sure that your masses are in kilograms and your velocities are in meters per second. So to quickly summarize the math, why is the answer definitely not the building? It's not moving, and if it's not moving, it's pretty easy to stop because it's already stopped. So it doesn't matter how much mass something has, if it's not moving, it has no momentum. Next is the arrow, which you know, this is faster than any arrow should reasonably shoot. That's about Mach 3, if I'm being honest. However, mass is teeny tiny. And what did I say about grams versus kilograms in this class? We always want kilograms. How many kilograms is 10 grams? 0.01 actually. Grams are 1,000 times smaller, so you divide by 1,000, drag the decimal point 1, 2, 3 places over. So 10 grams is 0.01 kilograms. So 0.01 times 1,000 is only 10 kilograms per second. The dog is actually the one where I gave you both units in their correct units already. So 25 times 10 is 250. And then the car, second biggest mass present, but it is idling forward very slowly. 1 centimeter per second is like the slowest idle speed I can imagine. Like you're in gear, but you take your foot off your gas and you're just snail's pace forward. How many meters are in a centimeter?
A lot.
It's actually the other way around. There's 100 centimeters in 1 meter, therefore there is 0.01 meters per centimeter. So 1 centimeter per second is 0.01 meters per second. And so 2,000 times 0.01 is only 20. I'd say this car is moving slow enough that you could probably put your foot on the bumper and it would stop. I wouldn't recommend trying it, but you probably could. And in an interesting twist, the dog wins this one. I have 2 dogs, and the younger one, I call her a puppy, but she's technically not. She acts like one, even though she technically isn't, I guess, but I'm gonna call her that anyway. The puppy is about 50 pounds in a torpedo shape, pretty low to the ground. If that dog was running at me full tilt and hit either my leg or my chest, I am hitting the ground. That dog is hard to stop, and I know from experience. So yeah, dog wins. Now, if the car was moving, it'd probably win. If it was like moving at any reasonable speed, it would be the hardest thing here to stop, but it's not. And the building, again, if the building's moving, you're having a bad day. Buildings shouldn't move. So, sound all right for now? All right. A couple small details that I'll just mention as you're packing up. Bless you. Again, the formula is mass times velocity, so if you have a lot of either of those things, you tend to have more momentum. I wouldn't want to get hit by a cheetah or a boulder, if I'm being honest. This is why trains are especially dangerous. They have a lot of mass and a lot of velocity, which is why I put that scene from Incredibles on the title slide.
I'm gonna start with that.
And that's because Spider-Man has super strength and webs. Last point I want to make for today is just to point out that momentum and inertia are similar but not the same thing. Again, inertia refers to Newton's first law of inertia. Object at rest stays at rest, object in motion stays in motion, which covers a very similar thing as momentum. If you have momentum, you want to keep moving in the same direction at the same speed. If you have inertia, you want to keep moving in the same direction at the same speed. But they are different, frustratingly. One, inertia is a scalar and momentum's a vector. So if you're moving north, your momentum says keep moving north. If you're moving north, your inertia just says keep moving, period. Secondly, and this is the big one, you have inertia when you're stationary. Because inertia is, if you're at rest, you stay at rest. If you're in motion, you stay in motion. But if you are stationary, you have no momentum left. So momentum ramps up from 0 to something when you move, but inertia is just consistent as long as you have the same mass. So you have inertia at rest, you don't have momentum at rest. That's the key difference. So they are similar but distinct. Questions? All right. Rest of this week we'll be talking about this. Let me know if you need anything. Attend lab as normal. There isn't a Friday lab. Yeah, it's only Monday, Tuesday, Wednesday.
You know, some of that was faster than car.
You could actually. Like, Tuesday and Wednesday are full, Monday's the emptiest one. So,
What you say?
Let's show you
Don't let that video catch you.
yeah, normally jumping between labs, like, most of them are full, but Monday's kind of the weird exception, so that'll be totally fine.
Welcome.
Is there any possible way that this lab